Welcome to this video in which we will look at vectors. So vectors are a mathematical object for quantities where you do not only have a size, like time would be only a size or mass would be so many kilograms, but where you also have a direction. So for instance, velocity or force. So if you're driving, cycling, walking around, you're not only interested in how fast you are going, how many kilometers per hour, but also in which direction. And for that, we will be using vectors. So let's look at a quick outline of my presentation here. And I'll switch here. So I'm first going to make clear when vectors are useful to work with by landing an airplane. Then I will introduce vectors in two spatial dimensions and operations that we can do with them. And then we will go to 3D and also I will show an application there. So let's first look at an application where you may be needing vectors. So what I'm going to look at is the example of landing an airplane. So here you have two video clips. And what is going to happen in this video clip is that we're going to land an airplane, but there is one difficulty because there is a very strong crosswind. So what does that mean? If you think about an airplane approaching a landing strip, so say the airplane is approaching like this and the airstrip is in this direction. And if there is a very strong crosswind, then the pilot needs to compensate for that. So what he does is that if the wind is from this direction and he wants to land on the landing strip in that direction, that he turns the aircraft a little bit like this and he compensates like that for the crosswind. So here I have two movie clips, and the first one that I'm going to start now is from a pilot who did not pay attention in his calculus class. And what you see here is that indeed he's approaching the landing strip. But as you can see, so he chickens out here. So he's not very convinced that he's going to land, and he starts up again. So imagine being in that airplane and you know that this is going to repeat itself if he's going to try it for a second time, and he wasn't very convinced the first time, so I would get pretty nervous, I think. Now, the second pilot does know how to do this. So you see that it's a huge airplane, and this pilot knows how to do his job. So we are going to switch camera positions in a second. Let's see, and here we can see the landing strip. In a second, you see, and indeed the airplane is turned. So it is not going directly towards the landing strip, but he compensates for the crosswind. And as you can see here, he lands perfectly. And this is just a very good landing. So how can you describe this mathematically? As you can see, the direction here is very important. So what we are going to do is, well, basically you have the landing strip here in this direction. The airplane compensates for the airspeed, and the airspeed, so the crosswind, is here. This is not my picture, I stole that from this website. This was on Gizmodo. And what you see here in this little diagram is that the airplane has a velocity in this direction of 250 kilometers per hour. But this 250 kilometers per hour has two components. It has a component in left to right direction here of 235 kilometers per hour, and it compensates for the crosswind here of 85 kilometers per hour. So as I said, what you need to describe this in mathematical terms is that you need not only the size of the velocity, so the 250 kilometers per hour, but you need to have this decomposition into two directions. So let's study how you can describe that mathematically. So for the airplane, we were talking about velocity. And more generally, you could also consider acceleration or maybe force. But what you do in mathematics is that you describe them with an arrow like you see here. So I have just a horizontal axis, a vertical axis, and now I'm going to draw an arrow that starts in the origin, and it has a horizontal component which is labeled A1 here, and a vertical component which is A2. So we do not only have a size, so the size or the magnitude would be the length of this arrow. If you make the arrow twice as large, it means that the velocity would be twice as large, but it also has a direction here. So the way we write this mathematically is that we have a boldface A, as you can see here. And of course, when you're doing handwriting, that is not so easy. So in handwriting, what I do is I underline the A to indicate it's a vector. So I say that A has two components, and in the slides, and usually I will write it like this. The book also uses the notation A is, and then pointy brackets like this. So both notations occur in textbooks, and sometimes also in textbooks. Let's write that in red because I'm not going to be using that. Is something like this, or you can also see something like this. So there are many different notations for vectors, but I'll be using this notation. So boldface A or underlined A in handwriting, and I write the components like this. So on top of each other. Rewrite it like this. So A is an element of R2. So A is an element of R2, and then the 2 indicates that the vector has two components. And in many applications, we will be using the length of the vector, and the length, that's just Pythagoras, is the square root of A1 squared plus A2 squared. So if you see this notation, so double vertical lines in handwriting like this, that means the length of the vector. Okay. So now we have vectors and we would like to do stuff with them. So if you have two of them, you can add them together. So here I have drawn a vector A and I've drawn a vector B, and then the sum, so we add them together. That is, if you make a parallelogram like this, so basically you take this vector B and you copy it to this location, and then you point at this point, which is the diagonal of this parallelogram, and this vector C here is called the sum of A plus B. So we have C equals A plus B. And if you're working with them, so if you have the components in numbers, you just add them together. So if you have 1, 2 plus 3, 4, you just do 1 plus 3, 2 plus 4. So we get the new vector 4, 6. So that's how you add vectors, very simple. The other thing that you can do with vectors, if you take one vector and you multiply with a number, and that's called scalar multiplication. So that's this box. Scalar, that just means number. So we have a number, C, a real number, and we multiply the vector A with C. So C times A. So if you have the original vector, you could see that as 1 times A. The blue vector here, so this whole vector here, that is 2 times A. And if you multiply with a negative number, like you see here, minus A, then it starts pointing in the other direction. So if you have a vector and you multiply with a negative number, it points in the opposite direction. And the length of a vector, if you multiply with C, take care, is the absolute value of C times A, because lengths are always positive numbers, or 0. And this black vector, minus A, has the same length as the red vector A. So you should put absolute value there. Now, the nice thing is, if you have this, you can already talk about the distance. So if you want to talk about the distance between point A and point B, what you can do is take the length of A minus B. And we know what it is now, because, well, minus B, that's minus 1 times B. And then we have this formula, and that should look familiar because we have already discussed, if you take 2 points in space, what the distance is. and you see that recovered here. Now, what more can you do with vectors? You can say that two vectors are parallel. So basically, if I have two vectors, I can say that they are parallel. That means that one is a multiple of the other. So here I let them leave from a different point, but normally we always let vectors start at the origin. And then we say that A and B, two vectors, are parallel if B is some multiple of A. Now there can be three situations here. If I draw a vector A, then I could multiply that with a positive number. So here we have B is C times A with C some positive number. It's even bigger than 1 here because I made the vector longer. We could also say, well, I have this vector A, and let's do that in a different color. I let B point in the opposite direction. So here we have B is C times A with C negative. And the third case, well, if C is positive or negative, C could also be 0. So then we have a vector. Oops, I wanted to do that in blue to keep it consistent. We could also say I have a vector A, and then I have a new vector. Let's make that one green, but that you don't really see this. So B is 0 times A, which is the 0 vector. And note that I underline the 0 to indicate that I mean the 0 vector. So the vector with components 0, 0. So these are the three situations that can occur then. Either A and B are pointing in the same direction or in opposite directions, or B is the all 0 vector. So apparently the 0 vector is parallel to any vector. I mean, that's not a very interesting statement, but according to this definition, this is what's true. So they can have the same direction, C is positive, opposite direction, C negative, or B is the 0 vector, and then B is 0, 0. Note that also here I put a bold 0 to indicate we are talking about the 0 vector. Some vectors are special. We like to work, and why will become clear a little bit later, with vectors that have length 1. So for instance, you already know many vectors that have length 1. If you have like a coordinate system with an x-axis and a y-axis, then for instance you could take the vector, this one here, which is the vector 1, 0, and that one has length 1. If you look at the distance from this point where it's pointing to the origin, that distance is 1. Also this vector 0, 1, that also has length 1, and I can continue like this. For instance, I could also look at this vector here, which is -1, 0, that has length 1. And let's do one more. Let's do that in orange. So I could also look at the vector 0, -1, and all of these have length 1. Of course, there are many more, right? So here I put a couple of examples. So ones we have already seen, 1, 0, 0, 1. But you could also take this one, a half square root of 2, a half square root of 2. Because if you look here, then this vector A, the length of that vector is the square root of a half square root of 2 squared plus a half square root of 2 squared, which is the square root. A half square root of 2, square root of 2 times square root of 2 equals 2. And divided by 4. So this is half plus a half is the square root of 1 is 1. So indeed this has length 1. And similarly, if you compute the length of this B vector, you also find that. And in principle, any vector of this form, cosine alpha, sine alpha, will have length 1, because cosine squared plus sine squared equals 1. That's great. You could also wonder if I now draw a vector here. Say I draw the vector with components 4 and 3. Let's call that x. This notation is not very important. This means just I call this x. That's why I put the dots there. That's standard math notation. It's not important that you know it, but I used it without thinking. So now we have a vector, and of course this does not have length 1, right? Because if I compute its length, then you will see that the length of x, that is the square root of 16 plus 9, which is the square root of 25, so that's 5. Now, you could wonder, can we create a new vector that points in the same direction? Let's call this vector u. And I would like to have u length 1, so pointing in the same direction as x, but then with length 1. If you think a little bit about that, then you could say, well, I'm going to pick u is 1 over 5 times 4, 3. And this vector works. And why does it work? Well, there is 2 ways you can look at that. So let's erase this again, then I have a little bit more writing space. So one way to look at that is say, well, the length of u, that's the square root of 4 over 5. If you square that, you get 16 over 25 plus 9 over 25 is the square root of 25 over 25. Well, that's 1. So indeed it works. The other way you could do that is that you could say, well, my u vector is 1 over 5 times my x vector. That means that the length of u is 1 over 5 times the length of x, which is 1 over 5 times 5, which is 1. So apparently, if I make this a little bit more general, if I have any vector x with a certain length, and then I define u to be 1 over the length of my x vector times x, then I find a unit vector. So this is a standard way how you can construct a unit vector from a given vector. And I put that in a separate theorem, which is also in the textbook, how to construct a unit vector. So if you pick a non-zero vector x, if you start with the 0 vector, this is not going to work, right? You can never multiply the 0 vector with a number to make it have length 1. So we start with a direction, and then if we construct this new vector, then it has length 1. And why that is true, we have just seen in an example. Now I started the definition of vectors by saying that you can specify a vector giving its x and y components, so these two numbers, so here the numbers 2 and 2. There is an alternative description, because you could also say that for this vector a, it is also completely specified if I tell you the angle that it makes with the positive x-axis plus its length. So this length is, let's call that r. So if I give you the angle and I give you the length, that would be an alternative description of the vector. So for this particular vector, you see that it has a length 2 square root of 2. So that's just the length of a. The length of a is the square root of 2 squared is 4 plus 2 squared is 4. That is square root of 8. 8 is 2 times 4. So that becomes 2 square root of 2. And the angle we often call that theta, so the Greek letter theta. And here you see that this angle for this particular vector is pi over 4. So let's do that for a couple more vectors. So here we have a vector b, which has horizontal component 0, y component 4. So you immediately see that the length is 4, and the angle that it makes with the positive x-axis is 90 degrees. That's pi over 2. So b has length r equals 4, and the angle is pi over 2. Next one. We just move in anti-clockwise direction. So here we have minus 3 over 3. The length is the square root of 9 plus 9. And the angle that we have here, well, that's 90 degrees plus 45 degrees, or pi over 2 plus another pi over 4. So what we find here is 3 times square root of 2, and the angle is 3 pi over 4. Next one, d, minus 5, 0. You immediately can tell that the length is 5 and the angle is pi. So length is 5, angle is pi. I think I have 2 more. I also have 0 minus 2. Well, that's pointing down. So the angle is 3 pi over 2, or minus pi over 2 if you like. You can either go this way or you could go this way. And the length is 2. So I put minus pi over 2 here. And this form, so this alternative form that we do not specify the 2 components, but we specify the length and the angle, that is called the polar form of a vector. So here in general, if you have a vector A with components A1 and A2, you can alternatively write that as r cosine theta, r sine theta, where theta is this angle and r is simply the length. So if you want to compute r and theta from A1 and A2, then you use this formula for r. The angle is a tiny bit more complicated, so you have to think a little bit here. So there is no direct formula for theta, but you just know that the tangent of theta is A2 over A1. And it's best to draw a picture like this to see what theta is exactly then. Now, this was all in 2 spatial dimensions. Of course, the world around us is 3D, has 3 spatial dimensions. So we can generalize this also to 3 spatial components. So how does that work? Well, then we have an x, y, and z-axis. If we take a general vector, we now have 3 components here. So we write that the vector is in R3. The length, we use the same notation, but you see that there is now an additional A3 squared under the square root sign. Adding them, same as in 2D. Scalar multiplication, multiplying A with some number C, goes the same as in 2D. In 3D, we also have these kind of standard vectors that we often use, and they are either indicated with E1, E2, and E3, or with I, J, and K. And they are called the standard basis, and the reason is that you can write any vector in terms of them. So if you pick a vector, say the vector minus 2, 3, and 5, then you can write that as minus 2 times the vector 1, 0, 0, plus 3 times the vector 0, 1, 0, plus 5 times 0, 0, 1. So if you pick these 3 vectors, you can write any vector in space as a combination of them. And such a combination is called a linear combination. Now, here is a little application of something that you can also do using vectors, points in space, distances, what you have seen. So what you see here is a little application. It is an old exam question where it says that we have a museum, and the museum would like to provide visitors with information on the art collection, and it uses small beacons that communicate with the visitors' smartphones. So if a person's smartphone is near a beacon, so just to explain, here we have a statue that is interesting. There is a little beacon at this position in the room. And if you get close to it, so what is close? Well, you can choose that. Then you get the information. So the phone can measure then the distance between the beacon and itself. And the idea is now that if we have a room that's 12 meters wide and 10 meters high, so this distance here is 12 and this distance here is 10. In the middle of the room is a statue. And then the question is, so if a visitor is closer than 2 meters to the statue, so we have the statue and you could draw a circle around it, and the radius of this circle is then 2 meters, then you get information about the object. So you walk there, you watch on your phone, and as soon as the phone gets sufficiently close, 2 meters to the statue, then you get information. So what is being asked here is give the inequality for the coordinates x, y of such a person. So we know the coordinates of the statue. The person has coordinates x, y. What condition should hold for x and y to get the information? So what you have to write down is an inequality that says that the distance between the statue and the visitor is less or equal to 2 meters. So I'm going to leave this to you to solve. If you have any difficulties, let me know. And there is a follow-up question. So to find out the precise location of a person, so say there are more objects and you would like to know precisely where a person is, you could also place beacons at the two corners A and B. So if I place a beacon here and a beacon here, and then I have a person that is in the room, apparently if you know this distance and you know this distance, then you should be able to tell where the person is in the room. So if this distance is square root of 13 and square root of 109, these are of course very silly numbers, but the reason here is that you find nice x and y positions. It's a bit cobbled up like that. So what are the x and y coordinates of the person? So try to solve that yourself. If you run into any difficulties, let me know and I'll help you along. Then last topic of this video, the equation of a sphere. So we are back in 3 spatial dimensions. And then if you take 2 points in space, so you could also say that I have x, y, z coordinates. I have a point P somewhere and I have a point Q somewhere. Then the distance between P and Q is this formula. It's basically the distance of the, if you would take the vector pointing to, let me write it down. If you would call this vector A, if you would call this vector B, then the distance between P and Q is the length of A minus B, or if you like, the length of B minus A. That's of course the same, right? The distance from P to Q is the same as the distance from Q to P. So if we use that, then we could look at this question. So find all points in space with a distance 2 from the origin. So again, let us draw x, y, and z axis. The origin is here. And now I'm interested to find points at a distance 2. So of course, for instance, here on the y-axis, so at 2, there will be a point that satisfies this condition. I have the same here on the x-axis and here on the z-axis. I could also go backwards like this. So if I continue these axes, then I could also have here on the z-axis at -2, or on the y-axis at -2, or on the x-axis at -2. And if you think a little bit more, this full circle here are all points that have distance 2 to the origin. I could do the same here, and then you get something like this. So what you see, and let's also draw this circle then, like that. So probably you believe me that all of the points that have a distance of 2 to the origin, they form a sphere in R3, a ball. So here is a nicer picture of all the points that have distance 2 to the origin. And the formula for that, well, all points P with coordinates x, y, z that have a distance to Q, and Q is 0, 0, 0, the origin of 2. The distance between P and Q equals 2. That is saying that this is the distance between them, and that should be equal to. So we find the equation x squared plus y squared plus z squared equals 4. So that is the equation of a sphere with radius 2 and center 0, 0, 0. Now, you can easily generalize that. If I would not pick a radius of 2 but a radius of r, then I would find r squared here. And if I would not pick 0, 0, 0, but for instance a, b and c, 3 numbers, then I just move the ball in space to a different position, and what you find then is the standard form of the equation of a sphere in space, which is x minus a squared plus y minus b squared plus z minus c squared equals r squared. So that is the equation of a sphere in space. It says the standard form because, as you can imagine, you can write it in different forms. So, for instance, if you look at this here, I could write that as x squared minus 2ax plus a squared. And then you get something different. So let me give one example where it is given. So I'm going to do that on a new piece of paper. Let me get some space here, like this. So you could imagine that we have the following equation given: x squared plus y squared plus z squared minus 4x plus 8y minus 10z plus 36 equals 0. And it is given that this is a sphere. And the question is, what is the standard form? Because if I now have this equation here, it is not immediately obvious that this is a sphere. Also, I don't know the radius and I don't know the center point. So if you want to have these two things, you need to do some work. So what we are going to do is first I'm going to collect the terms with x in there. So I have x squared minus 4x. And what I would really like is it to be in the form x minus a squared, because that is in the standard form. Now this is the same as x squared minus 2ax plus a squared. So apparently if I want this thing and this thing to be the same, I should pick a to be equal to 2. Because then I have here x squared minus 4x plus 4. So what you see is that apparently x squared minus 4x, that is the same as x minus 2 squared. Well, almost, because here, if I start with x minus 2 squared, I get an additional plus 4. So if I subtract that, then they are the same. And you can easily check that. So this is maybe going a bit fast if you have never seen that before. But if you get rid of these brackets again, you get x squared minus 4x plus 4. And then with a minus 4, you have precisely what it says here. I can do the same thing for the y. So I have a y squared plus 8y. So on the one side I have y squared plus 8y. On the other side I would like to write that as y minus b squared. That's y squared minus 2by plus b squared. So what you see is if I want them to be the same, I should pick b equal to minus 4. Because then if I make that choice, I get y squared. This becomes plus 8y, what I have here. And this one is still left here. So apparently, let me still write that on this slide, but then I need a little bit more space. So let's move everything up a little bit. So apparently, y squared plus 8y is the same as y plus 4 squared. So that's what we have here. But then this b squared, that is not there. So minus 16. And again, if you don't really believe me, if you get rid of the brackets here, you get y squared plus 8y plus 16. And then with the minus 16, we are in good shape. Finally, I have z squared minus 10z. Oh, I should do that in a different color, sorry. Z squared minus 10z. So let's do that on a new slide. So I have z squared minus 10z. I would like to write that as z minus c squared. Z squared minus 2cz plus c squared. So if you want them to be the same, you should pick c equal to 5. And then what we find is that z squared minus 10z is z minus 5 squared minus 25. This thing, what I did here, so basically this rewriting from here to here, that is called completing the square. Completing the square. So this is the square that has been completed then. So let's wrap up what we found. I'm going back to the previous slide for a sec. So apparently this x squared minus 4x. So let me just copy that here. So we had x squared minus 4x. Going back here. So I'm going to write the original equation, but I'm just going to change the order a little bit. We have plus y squared plus 8y plus z squared minus 10z plus 36 equals 0. So that's the original equation, but in a different order. X squared minus 4x. I have found here that I can write that as x minus 2 squared minus 4. So let's copy that. X minus 2 squared minus 4 plus, with the y's, we found y plus 4 squared minus 16. Yeah, and then plus z minus 5 squared minus 25 plus 36 equals 0. And then we're in pretty good shape, as you see, because what we have now found is x minus 2 squared plus y plus 4 squared plus z minus 5 squared. All the constants I add together, so I have minus 4 minus 16 is minus 20, minus 25 is minus 45, plus 36 gives minus 9, and if I move that to the right hand side, I find a 9 here. So apparently what we have, this is the standard form for a sphere. We know that the center of the sphere is 2, minus 4, and 5. And the radius, r, is the square root of 9, is 3. So you see that now we have all the information we would like. If we would like to make a plot of this, we know what the center is and we know we get a sphere, and that sphere has radius 3. So completing the square gets you from a non-standard form equation to an equation that is in standard form, and from that form we can have all kinds of interesting information. That wraps up this video, so let's make a short list of what we have seen. So we have seen that you can use vectors either in 2D or in 3D for quantities that have a direction and a size, such as velocity or force. Working with vectors, if you have two vectors, you can add them together. If you have one vector and a number, you can multiply them. We have seen that you can also use the polar form, where you specify the angle and the length. And we have looked at the equation of a sphere. So I hope all was clear, and have a great day, and I'll see you in the next video.